Hi, this is Maha Muntasser, Associate Professor at Structural Engineering Department, Faculty of Engineering, Cairo University. I will be presenting today a topic related to a rehabilitation study of an old metallic orthotropic deck bridge on behalf of myself and Dr. Hussein Abbas from Al-Azhar University. The outline of the presentation will start by an overview, followed by historical background and brief description of the case study, and then inspection and the observed effects, followed by analysis and the required repair works, and finally conclusions for the performed work. The photos show samples of different metallic bridges in Egypt, employing structural systems including trusses, arches, plate girders. Some of these bridges has been in service for more than 100 years, and based on this they were subject to inspection and related repair works. Metallic orthotropic deck bridges represent an efficient structural system in many roadway bridges due to the large reduction in bridge dead load. This system was used in many intersections in Egypt, considering the quick erection of the system, and this helps to avoid any traffic congestions at the busy locations in Egypt. In this study, we focused on Sayeda Eisha Bridge, which is an orthotropic metallic deck bridge. And considering the rest of the presentation, we will be showing the structural system with the details and the details of the inspection study, analysis, and all related items. Sayeda Eisha Bridge is located on Salah Salim Street, one of the busiest areas in Cairo. It was constructed in 1970, and it is composed of a metallic orthotropic design, following a standardized design of dismountable steel viaducts. This was a byproduct of a competition launched by the French Ministry of Equipment. Sayeda Eisha Bridge was meant to be a temporary solution to solve a problem at the area, and then to be dismantled afterwards, but it has been in service for around 50 years. The bridge has a problem of a sharp curved part. This sharp curved part doesn't include the required super elevation, which resulted in many accidents, including vehicles falling from the bridge surface. The bridge is actually composed of two adjacent bridges, 2 lanes for each, with a total length of approximately 300 meters. The length is divided between 13 successive bays, serving traffic flow in both directions. The span of each bay ranges between around 23 to 25 meters. Each bridge has 4 main beams, spaced at 1.75 meters, and the spacing between the center line of the main girder of one bridge and the additional bridge is 2.5 meters. These main beams are supported on steel moment-resisting frames that are repeated at several spacings. The orthotropic deck is composed of a steel plate strengthened with ropes, and these are supported on cross beams spaced at 3 meters and supported on the main beams, as can be seen from the photo. The main beam cross-section decreases at the support on the top of the girder at the moment-resisting frame, and it is mainly a shear connection. At the moment-resisting frame, there are also pipes that are used to support the frame in the longitudinal direction in order to provide stability and resist any longitudinal forces from braking forces, for example. The inspection campaign started by studying all the documents that were found for the bridge. Any missing dimensions were measured from site, and then the inspectors focused on many items, including if there is any corrosion and the condition of the painting, if there is fatigue defects, how are the condition of the rivets and poles, bearings, and if there is any collision or impact damage within the bridge. The observed defects included corrosion at bottom of columns below the ground surface for most of the columns within the bridge, Also, there were many missing poles within many connections, as seen in the second photo. Some of the elements were not straight, vertically straight for columns or horizontally aligned for beams. So there were some deformations in the steel elements, permanent deformations that causes changes in the shape of the structural part other than what it was meant or designed for. Also, there was increased spacing between bridge bars at some locations, loss of asphaltic layer on top of the orthotropic deck, guardrail was missing at some locations or deformed at other parts, and also there was accumulation of garbage below the bridge. The condition of the foundation was missing, so excavation works were performed in order to explore their type, and the maximum depth of foundation was found equal to 5.5 meters. The footings are composed of two reinforced concrete footings supporting two steel columns and connected with a concrete girder, and these two footings are supported on a concrete plain mass taking a circular form as can be seen here. Following the inspection work, a detailed analysis was performed, followed by proposal for the repair works for the considered bridge. A 3D grillage model was built using SAP 2000 software, including the main beams, the cross beams, and the moment resisting frames. And this model was subjected to the design loads as per the last version of the Egyptian code. These loads include three main lanes, one including a truck of 600 kilonewton weight and the other 400 kilonewton and the last one 200 kilonewton. These loads are higher than the loads that usually bridges were designed for, and based on this the internal forces at different locations was determined considering the different elements, main beams, cross beams, moment resisting frame including the girder and the column. Based on the analysis, many observations were found, including stresses on some members and connections exceed the allowable stress values according to the Egyptian code. The number of poles in some connection is not sufficient to resist the applied shear or moment value, and strengthening applications has to be performed, but it has to consider that the weight of the bridge has to be in a certain range due to the critical condition of the foundation. Also, any repair applications has to consider that hindering the traffic flow will be also critical. So, considering this study, there were two main limitations: to apply repair mechanisms or repair applications that doesn't affect on the traffic flow, and also to consider the lowest possible addition of elements with the lowest possible weight. Accordingly, the main beams were strengthened by adding bottom plates to decrease the stress level within them. The cross beams were strengthened by adding diagonal braces, as can be seen from these two photos. For the columns, the corroded parts were removed and then plates were added to make up for any decrease in the thickness of the plates due to corrosion. And also the connection between the base connection was strengthened by added anchors, and then a concrete encasing was added around the bottom part of the columns. The spacing between the different orthotropic decking plates was filled with the proper material to act as an expansion joint, and the asphaltic layer was removed and replaced by a new one. Based on this study, it was found that there was many defects for the inspected bridge, including corrosion, increased stresses in members and connections, deformation in some elements, and these defects were discovered during a complete inspection of the bridge that started by studying the design drawings. Not many design drawings were found, so many elements were measured on site, and based on this, a finite element model was built and subjected to loads. Based on the analysis, strengthening applications were planned and corrective actions were proposed. These chosen actions were considered based on some limitations, considering the sensitivity of the bridge location within a busy area, in addition to the critical condition of the foundations that didn't allow for increase in the bridge on width. Thank you for listening to this presentation, and if you have any questions, I will be available during the live question and answer session.